Alright,
Is that like
today we are going to take a look at particle motion again. We spent a few days doing a lot of particle motion stuff with derivatives. And now we're going to add in particle motion stuff with integrals. So with this, we'll also kind of review the stuff that we did with derivatives. So the big idea that we're going to use a lot is the fundamental theorem of calculus, which we hopefully know that by now. Did that in the warm-up. The two new ideas here. I didn't think it was that one. The two new ideas here, are this: displacement and total distance traveled. So a lot of the time, you are going to be given a velocity function and asked for information about how far the particle has traveled or where the particle is. Displacement, or you may see this called net distance. Displacement or net distance talks about where a particle is relative to where it started. So let's say I'm right here at the origin, and I walk 3 steps to the right. And then I walk 2 steps back to the left. My displacement would be 1. I'm 1 spot away from where I started, 1 step away from where I started. But my total distance would be 5. I took 5 total steps, but I only ended up 1 step away from where I started. That's essentially the difference between displacement and total distance traveled. To actually calculate that, if we're given a velocity function, to get displacement, all I'm doing is taking the integral of that velocity function. Just like we had been doing with any random rate function. Integrating a rate gets us an amount. Same thing here. Integrating a velocity function gets us a distance, a position. To get total distance traveled, I would integrate the absolute value of velocity. So that's the key difference here. To get displacement, or net distance, we just integrate velocity. To get total distance traveled, we integrate the absolute value of velocity. So graphically, if we've got something like this, we're saying this is our velocity function. If I want to get displacement, I would say, well, I went this far to the right. And remember, if velocity is positive, that means we're moving to the right. Then I went this far to the left, and then this far to the right again. So my displacement, I would take this minus this plus this. To get total distance, I would just add all 3 of these distances together. And I'm thinking about the absolute value. So what I'm really doing is flipping this piece up, saying, well, I traveled this far. Questions so far? All right, let's do an example then. So down here, we are given a velocity function. It says a particle is moving along a line, so that its velocity is given by t cubed minus 9t squared plus 15t plus 10 feet per second at time t. So we just want to find the displacement and the total distance. So displacement on the interval 0 to 5 is just taking the integral of this function on this interval. So t cubed minus 9t squared plus 15t plus 10 dt. So again, just to be a little nitpicky, don't forget your dt. And when we write the integral, we need to show that that dt is being multiplied by the entire function. They will dock you points on the AP test for not writing that correctly. So make sure that we're writing our dt and showing it's being multiplied by the function. So if I wanted to do this by hand, how would I do this?
you plug in?
Not yet.
You put the antiderivative?
Right. You need to take the antiderivative, and then plug in 5, plug in 0. So what would my antiderivative be?
1/14 minus 3. Yeah, 30.
Nine divided by 3 is 3.
15 over 2.
We're evaluating that from 0 to 5. So again, remember the notation. After we take the antiderivative, we're no longer using the integral symbol. We're drawing a line at the end, showing our bounds, saying these are what we're going to evaluate. Okay, so again, make sure you're not writing the integral symbol after we've taken the antiderivative. So now, I'm just plugging in 5 into all this. So 4 times 5 to the 4th minus 3 times 5 cubed plus 15 halves times 5 squared plus 10 times 5 minus, and if I plug in 0, all of these terms would be 0. So I'm not going to write it all out. Just minus 0 in this case. So this would be kind of ugly to evaluate by hand.
But it's kind of our answer, right?
Yeah, I mean, technically, if this is a free response, we can leave it like that. Right? We have all numerical values. Okay, that's an acceptable answer on the free response. Okay. But let's get an actual answer here. Let's get one number. So we can plug that into a calculator. What would we get here? Let's see if I can do it faster. I hope you can plug this into the calculator faster than I can do this in my head.
I suppose it's right.
Watch I plug it in wrong.
So that's just 25 fourths. Is that right? Yeah,
Wait.
I tried.
No. You're wrong.
What did you get? I didn't plug it.
Just leave the Z. I got 18 points.
Oh, yeah. That's 950. So that would be 75.
There you go. That's correct.
I got rid of that 50 somehow.
I still hate how you can do that in your head.
Oh, you went to college for math.
Yeah, it's not anything easy. It's just. So, what would my units be here?
Feet squared. No, okay.
Just feet. Right? If our velocity is feet per second, position, right? If we're integrating, we get position. So that would just be 75 over 4 feet, or 18.75 feet. Or 25, whatever it was. 75. Are we okay with that one? Alright, then the second part asks for the total distance traveled. Now, since we did this by hand, we could actually, well, actually, no. Never mind. That wouldn't work. To get total distance, we want to integrate the absolute value of velocity. Right? So I'm taking this integral and just throwing absolute value bars around my velocity function. The answer will not be the same.
Because
Yeah. So in part A, the particle moved left and right, okay, at different points. Here, we just want to figure out total distance, not where it actually is. So most of the time, you're asked to find the total distance that will be a calculator question, okay, because taking the absolute value of a function and figuring out where to split that integral up gets pretty messy. Okay, so we're not going to worry about doing those by hand. Okay, we're going to assume that if you were ever asked to find total distance, it will be on the calculator. Does everybody know where absolute value is on the calculator?
no.
Alright, so go to math, and then scroll over to the right one. So you should be under num. The first option is abs. That's absolute value. Okay, so you would do your math 9, put in your bounds, and then do math, scroll over to num, and then abs. That's how you get your absolute value, and then we can plug this directly into the calculator.
It's taking a minute to calculate. That's an ugly fraction.
It comes out as a fraction.
Yeah.
Let's stick with this. 54.833.
Thing is, on the cons, they wanted fractions, or you had to put in the whole decimal. I was rounding my decimals. They kept on yelling at me.
Yeah, they like exact answers. Did we get 54.833?
Let me see. What did you do? What did you do? That did it right.
I got 361.
Oh, you got minus 15x instead of plus 15x.
There you go.
Alright, questions so far? Alright, then let's do a quick review on things that we've already talked about. Alright. So, the big things that we've talked about with particle motion before are position, velocity, and acceleration. Okay, and then we threw speed in there as well. So, position, okay, usually expressed as s of t or x of t. Your hitter?
No, she didn't do it. Really, if you was trying to, you just it definitely was. And then if you right here, I was going down, not big enough. Like it's on the floor.
Try again.
I know.
How do you like break out? I have to start
This class is something on the Monday where math is right.
No, I'm not going. I just clicked it.
So when are you gonna take those vacation days and not be here?
I'm not going to do that.
My sister's fiance's mom has stipulated to make vacation and she gets to retire year early.
Sick days.
Yeah. That's what I said.
Vacation.
Yeah.
So how many?
For most people, like most professions, vacation and sick days are the same thing. For teachers, they're very different.
Well, you should take those sick days.
Not sick.
You should take them. So we don't have to do that.
Also,
Oh! No, it hit your binder.
Oh.
Should I use it? Isn't it your table?
Just look at my cool sunglasses.
Alright, what about average velocity?
It's
So what's the difference between average and instantaneous velocity?
this is over amount of time.
Average is like the average.
Yeah.
That's
Listen, Dinah has the answer, but she's just whispering it like she does.
Dana, just say it.
Right, yeah. Instantaneous would be the velocity at one specific time. Average would be the velocity over the entire interval that we care about. So how would I find average velocity?
Me, that's average.
That's
Average value.
average value. So
Look,
technically we could do that. I guess I should have been more specific. If we are given a position function to get average velocity, we want to take the slope of our endpoints. If we were given a velocity function, though, we would do that 1 over b minus a times the integral of the velocity function. But more often than not, if we are asked for average velocity, we will be given position. Right? So this is just slope. Okay, slope between 2 points on the position curve. Okay, if we want average velocity, we want slope between 2 points on position. Instantaneous velocity, then, like Dinah told us, is the velocity at one specific point. Okay, so this is where we would think about taking the derivative of position. Speed. Actually, I guess I did want to mention one other thing with instantaneous velocity. Okay, when our velocity is positive, what's the particle doing?
going to the right.
Yeah, moving. We either think about it as forward or to the right. Yeah, so when our velocity is positive, the particle is moving right, or we could say forward, right? And then when velocity is negative, the particle is moving to the left.
You should just put a punch. Or am I thinking of an electric slide?
Both line dances. Why do you want to play that?
Because it's moved to the right and moved to the left.
Yeah.
It's one of those three.
What about
How
when
did I jump?
velocity equals 0? What's going on?
It stopped.
Particle stopped. Right? So I should have left a little more room here. Particle is stopped or at rest. You might see it worded. Now, what about speed? What is speed?
It's not the derivative of velocity.
That's a value.
It is the absolute value of something.
Of velocity?
It's the absolute value of velocity. Speed is just directionless velocity. Right? It's the absolute value of velocity.
Acceleration is the derivative of velocity.
Right? Acceleration is the derivative of velocity. But first, on speed, okay, we talked about ways to determine whether something was speeding up or slowing down. So, do we remember how to determine those?
I'm trying to think. I think I remember this, but I don't know exactly what it is.
So, a particle is speeding up.
Oh, it's increasing.
If what's increasing?
A slope.
Of
Velocity.
yeah. Right? So, a particle is speeding up. Okay, there are a couple of ways that we can kind of word this. I think the easiest way to think about it is velocity and acceleration have the same sign.
Oh no.
So what that means in terms of a graph is if the velocity graph is moving away from the x-axis, either it's going up away from the x-axis or it's going down away from the x-axis. In that case, or in those cases, velocity and acceleration would both be positive, or velocity and acceleration would both be negative. A particle is slowing down when velocity and acceleration have opposite signs, right? Or in terms of a velocity graph, the graph is moving towards the x-axis. Right? And then finally acceleration, derivative of velocity, right, which would be the second derivative of position. So I'll write all of that out. So is this jogging some memories or remembering most of this stuff? Back slowly. All right, so then the next two are what we just talked about. Displacement and total distance. So just so we have all this information in one place, let's jot this down again here. So displacement is the integral of our velocity function. This tells us where we are relative to where we started. Total distance is the integral of the absolute value of velocity. And that's pretty self-explanatory, right? It tells us the total distance traveled. Now, a lot of the time we will be given a starting position. Right? So to get a final position, we take our initial position plus our displacements. that will get me final position. Okay, and this is, I mean, we worked with stuff like this when we did the rates right before spring break. Okay, we talked about, maybe there's initially 500 tons of gravel plants, or initially there's 30 pounds of bananas on display, right? Some initial value. Then we want to add how much that value's changed. That gives us the final value. Okay, we're just applying that to position now. All right. Questions? All right, let's do a few more examples here. So, first, an object is moving along the x-axis so that its velocity is given by 3t squared minus 10t plus 3, and we are given an initial position. Okay, we're told that the position of the particle at t equals 1 is 3. Right? So, part A just says find a position function for the particle. If I know velocity, how do I find a position function? Yeah, just take the antiderivative. And here we're not asked for total distance or net distance, we just want a function. So I'm just taking the indefinite integral of my velocity, 3t squared minus 10t plus 3. So what would I get? It? It's an indefinite integral, so we need plus c.
We have.
Yes. Whenever we are taking an indefinite integral, we need plus c. Okay, now, part B says find the displacement of the particle from t equals 0 to t equals 6. How would I do that? Just taking the integral from 0 to 6 of 3t squared minus 10t plus 3. Okay. So let's use the calculator here for time's sake. What would we get if we plug this into the calculator? And we are not given units here, so we can't tack on. We could say like 54 units. Right? We move 54 units. Then total distance. How do I do that? Integral of the absolute value. Right? So what would we get here? $72.963. Okay with that? Okay, on the next one, we're driving in traffic behind a bus going at 45 miles an hour. We finally get a chance to pass, step on the gas, and our acceleration then is given by this function, 4 over the square root of t. We want to figure out how fast we're going 16 seconds later. Okay, so this is kind of a different type of question. This right here is our initial velocity. Right? I start out going 66 feet per second. And then, at some moment in time, we'll say that this is at t equals 0. Right? Our our acceleration is given by 4 over the square root of t. How would I figure out how fast I'm going 16 seconds later? We will need velocity. We'll need to take the antiderivative of this 4 over t squared. And I'll go ahead and write it as 4 times t to the negative 1/2. What else do I need here? Yes, that we want to find displacement of velocity here to get my new velocity. So what I want here are my bounds, 0 to 16. So this is going to tell me how much my velocity changed over this 16-second interval. So what is this integral? We plug this into the calculator.
$31.999.
31.999. So this would be in feet per second, right? Because I took my acceleration function and took the antiderivative of that. So if acceleration is feet per second, the antiderivative velocity would be feet per second. So is this how fast I'm traveling after 16 seconds? Maybe. No, it is not. Why is it not how fast I'm traveling? Yeah, so how fast was I going at 0 seconds? 66. And I started out going 66 feet per second, and then I accelerated. And by the end of 16 seconds, my change in velocity was this much. So if I started out at 66 feet per second, I sped up this much, my final velocity would be 66 plus, we'll just round that to 32. And so my final velocity at 16 seconds would be 98 feet per second. Now, how far did we travel during that time? That would be total distance. Right. So we need the absolute value of velocity, right? Yes. So we will need the antiderivative of acceleration to get velocity. Then we will need to integrate that again. So if we're going to use our calculator to evaluate this part, we will have to do this part by hand to get what our velocity function would be. Okay, so first, I'll come over here and say that velocity is going to be the integral of this, right, of 4t to the negative 1/2 dt. Yeah, so how would I take the antiderivative of this?
Plus 1.
Plus 1, so I'd have t to the positive 1/2. Right, old coefficient over new exponent, so 4 divided by 1/2 would be 8. Right? So technically we would have a plus c here. Okay, but when we are, let's see, when we're taking our antiderivative of velocity, we don't need to think about that plus c. Alright. Oh no, actually we do. Sorry, that was a incorrect statement. We know what our plus c is. Right? Our initial value is 66. So we can say 18 to the 1/2 plus 66. Alright.
So that you have